Okay, I'm just going to finish the outline that we started on Friday so that it's all together in your notes. And then I'm sure. Uh, um, okay, so we've been going through an outline of topics so far. The last thing we mentioned was the work of expansion. So here's what you already have is uh, work of expansion. And then we talked about number 4, the first law of thermodynamics for closed systems. So that's what we've been doing with the first law this whole time. And the first closed systems means no material is entering or leaving the system. In other words, your system is just a defined amount of material. That's what you're always used to doing in physics is closed systems. You know, you have a single object or whatever, and you're doing Newton's laws or conservation of energy on this closed amount of material, this fixed amount of material. But pretty soon we're going to get into the first law for uh, first law. I'm blanking on the term, but where we're going to have, we're going to be, oh, volume, uh, why am I blanking on that? But we're going to, instead of be looking at a fixed amount of material, we're going to be looking at a set volume, a place in space. And in that place, material is going to be going in some inlet or multiple inlets and going out some exit. And so we're going to have to take into account the fact that the system we're looking at is not the same material. You know, it's some of the same material, some new material, and it's lost some old material. So that's the distinction between closed systems and control volume. That's what control volume analysis. Um, Okay, so first we did just the regular first law, which said the change in the energy of the system is equal to Q minus W. And one of the most important things to make sense out of in this class is the sign convention for the first law. We've talked about that a lot. So the sign convention makes sense if you think about what happens in a power cycle. Um, so let's imagine a cylinder with a piston, and our closed system is a gas. And we heat it up, and that makes the piston go up. And so heat in to the system, resulting in work out of the system. Okay, and so in a power cycle, your Q and your W are both positive. So that's what this sign convention is. You can always make sense out of it thinking about the power cycle. Um, and then the second one is this is like the difference form of the first law of thermodynamics. Then we also did the differential form of the first law, and that said dE dt is equal to Q dot minus W dot. And this time, Q dot stands for the rate at which energy goes into the system as heat, and W dot is the rate at which work is done on the surroundings by the system. So what is the difference between these two equations? The difference between these, well, so for A, you're talking about a process going from one instant to another instant. So you have two instants, okay? In the differential form, you're talking about a single instant, but you're talking about the rates of change, okay? But largely, we said that the differential form we're going to use with heat transfer. So that's not always the case, but often that's what we do. And that's because the heat transfer equations are given in terms of rates. So C is heat transfer. And there are three modes of heat transfer. The first one is conduction. And the conduction equation says Q dot is equal to negative coefficient of thermal conduction, kappa, times A times d temperature dx. And even though I'm always going to give you this equation with that negative, we're not going to use that negative. That's a direction thing, and we're going to get our directions based on what's the hotter side and what's the colder side. So forget about this. Just remember that heat only goes from the hot to the cold. Spontaneously, that is. You can make heat go from cold to hot, like in a refrigeration system, but you have to do other things. It's not going to happen spontaneously. Okay. And then this, we're always going to deal with temperature varying linearly with the distance through the wall or through the window or whatever. And so this will always just be replaced by a change in temperature over a distance that the energy has to travel.
Professor?
Yes.
So when you write minus and then like cross it out, so like we basically just figure it out from like the actual problem.
Exactly. Just come up with the magnitude of this Q dot, and then the direction just comes from which is the hot side and which is the cold side. Your system or the surroundings. Uh, the second mode of heat transfer is radiation. And that equation looks like this. Q dot emitted is equal to the emissivity, so that's white or black or where in between, times the Stefan-Boltzmann constant times the temperature to the fourth power. This isn't too useful to us in thermodynamics equations. So this isn't too useful in the first law. And the reason it isn't too useful is because in the first law, we need to know the net heat transfer. So if we only know the heat that's transferring out of the system, but we don't know anything about the heat that's transferring into the system, then we're missing a lot of stuff that we need. Okay, but there is a case where we can calculate the net radiation. And that's when you have a small system surrounded by a larger body. And in that case, you can think of this as the net radiation, the net heat transfer is equal to the emissivity times the Stefan-Boltzmann constant. I am missing an A in there. Sorry about that, making your notes look messy. But we have the emissivity times the Stefan-Boltzmann constant times the surface area of the object. And then same thing in here, emissivity, Stefan-Boltzmann constant, times the area of the smaller body, times the quantity, temperature of the body to the fourth, minus the temperature of the surroundings to the fourth. Okay, and you can just always arrange these so that this thing comes out positive. The sign doesn't matter here. You're just using that equation to get the net radiation.
When you say a small system surrounded by a larger body,
Yeah.
do you mean like an oven inside a cave?
Exactly. That's a good example. Yes, exactly. Or an object surrounded by the atmosphere. Yeah. The difficulty with that is the different parts have different temperatures and stuff, but you can do approximations that way.
So which one we are going to use often?
We're not going to use any of these too often, but let's see. What would be, I mean, it just matters. It just depends on the setting. I suppose you could say the one that generally is most useful probably is convection, because that's sort of like an experimental curve fit. So all the other stuff can be sort of built into it. Yeah. But it just depends on the, if you're trying to calculate the temperature of the edge of a pan handle when the body of the pan is over the stove, then conduction is what you're talking about. If you're talking about energy transfer from a fire to something, it's mostly radiation, Remember that radiation is electromagnetic waves. So this is transferred by electromagnetic waves. And also remember that whenever you're using these radiation equations, the temperature needs to be in an absolute scale like Kelvin. And then the last one is convection. And the equation for that says Q dot is equal to this constant H that you get experimentally times the area, but that's only the area that's exposed to the fluid flow, times the quantity temperature of the body minus temperature of the fluid. And so remember that this H is an experimental constant that you get for your specific setup. And as far as all of these heat transfer equations work, remember, for all the heat transfer equations, you can't trust the signs. That's different than, like, for example, the work of expansion. When you calculate the work of expansion, then that's just absolutely ready right there to plug into the first law of thermodynamics. But this, you have to think about the direction of the energy transfer. And the direction of the energy transfer is always going to go from the high temperature to the low temperature. So if your system, the thing you're isolating, is the lower temperature body, then you're going to make whatever magnitude you get from the heat transfer equations, you're going to make that positive when you put it into the first law. If your system is the high temperature, then heat is going to be leaving your system to the surroundings, and you're going to take your absolute value from these equations and make it negative to put it into the first law. Okay? Okay, that's the end of the outline of what we've talked about so far. Anybody have any questions or want to talk about any of these? Yeah.
This outline is for the exam, I'm assuming.
Well, yeah, I mean, it's not. I haven't even looked when the date of the first exam is. I think it's still a couple weeks away.
Oh, next Friday?
Oh, next Friday, a week from Friday?
Yeah, next Friday. Yeah.
Okay, well, I have to think about what topics. We'll probably have a little bit of newer stuff on there. But this thing is just kind of to help you organize the ideas in this class into your head. I think making these outlines in classes where you have a lot of small topics, this is one of them. Most of my classes are not really that way, but this is a class where it's just a lot of small topics, and a big part of the challenge is just organizing all these topics in your head, you know? And in classes like that, I think it's helpful to go through, do outlines, you know, do simplified notes, you know, read through your notes a lot. I've always found that to be the case. Like, for example, I don't know how many of you have taken Calc 4 yet, but when you take Calc 4, it's just throwing this whole list, like this whole toolbox full of differential equation techniques at you. And the real struggle isn't the mathematical, like, understanding really subtle things. The big challenge is just organizing this stuff in your head, knowing, like, when I see this type of differential equation, I use this technique, you know? And so that's another class where I think you'll find if you just keep outlining what you're doing, you'll be happy. Yeah.
I would definitely agree with that, because if you use the wrong sort of differential
Right.
strategy, then you get yourself into a
Exactly. Yep. Yeah, it's just totally about knowing. It's like a lookup list. You're like, okay, this differential equation I have fits into this category. It's a linear first order, and so linear first order I use integrating factors or whatever. Okay. So now let's go. Let's go back and I'd be happy to go through as many homework questions as people want. What are some of the ones? I think this was an assignment that people often find a little tricky. So
Number 3.
number 3, okay. Okay, so this is differential form of the first law, right? Uh, first law. First law. Oh, diff. Yep. Okay, so this is the one, the electric generator.
Is it the weekly? I'm talking about the weekly.
Oh, you're talking about the weekly. Okay, I can let me look at it, and I can give little hints, but the weekly ones are a little more sort of part of the evaluation, you know. So I don't want to like go through it the same way. Yeah,
Could we do the fourth one for the daily?
yeah. Let me look at this weekly one first. Okay, so number 3. Okay, so this is a polytropic process. And when you get these polytropic processes, what are you thinking you're probably, what technique are you thinking you're probably going to use there? You're probably going to have to calculate the work of expansion. Okay, so you're, so without even looking at this question, I'm sort of thinking, okay, I'm probably going to have to use what's given to come up with the pressure as a function of the volume so that I can use um, the integral calculation of the work of expansion. Okay, so I haven't even read the problem yet. I just saw that equation. Okay, this gas is insulated, so no heat transfer occurs. Um, so we know that Q is going to be 0. Okay, we know that we're probably going to have a way to calculate W. So all this is making us head towards using the first law. It gives you at an instant 1, you have a pressure and a specific volume. Okay, well, it does not give a mass, it looks like. So if, oh, okay, yeah, I missed it. Okay, so it gives you a mass. So you can always go from specific volume to volume if you have the mass. You're just multiplying the mass to the specific volume. Okay, so even though, so you'd get a wrong answer if you used the pressure and used this as a true volume. But you can use this, multiply it by this, and that'll give you a true volume. And then we have at state 2, we have a pressure, and we can get a true volume from this one. Okay, so we have pressure and volume at instant 1 and instant 2. Yeah.
Professor, so A and B are constants we need to find?
Yes, in order to get pressure as a function of volume, you're going to have to figure out what A and B are. And you're going to use pressure and volume at state 1 and pressure and volume at state 2 to get those. You have to do a little bit of exponent, algebra. But once you have pressure as a function of volume, then you can go to the first law, calculate the change in internal energy, and then go back to specific internal energy by using the mass again. Yep. Yeah. Okay. So you have an object with a given mass and a given height. and it starts out with a given speed. You have heat and work added, and then you're given a height and a speed at instant 2. Okay, so this one, let me write something down about this one. So weekly assignment 1, and this is number 2. Okay, so you saw these expressions a lot in physics 1, but they might not be right at the front of your brain. But remember that the kinetic energy is 1/2 times the mass times the speed squared. Let me write this with a different variable. So I'll call that capital S. Man, there's no good variables really to use here, but that's the speed. And then the potential energy, gravitational potential energy. That's why I didn't want to use V there. I usually use a capital V for speed, but the gravitational potential energy is the mass of the object times 9.81 meters per second squared times the object's height. And then remember that the energy of the object, capital E, is equal to the kinetic plus the potential plus the internal energy. Okay, so you can see how with this formula for gravitational potential energy, the height of the object is going to come in as h. Okay, the speed is going to come in as that capital S there. And then you can use that to calculate stuff about the internal energy.
Is it okay to use different variable like
Yeah, sure.
inside of T, would say that the difference in K or like
Yeah, but this is what I'm always going to use. I mean, I'm not going to use kinetic and potential energy too much in this class, but yeah. But these are the ones I'm always going to use, T and V, and then U is internal energy. Any other questions about that one? Okay. So then, are there any other weekly assignment questions you'd like me to say something about?
In number 1, is 1B, I got a mathematical solution. I think it came out as 85 rather than 35 degrees Celsius.
On the daily problem?
Yeah, on the daily level.
Oh, okay. Let me just make sure. Anybody have any weekly questions? Okay. So close that one. Look at the daily one. So now we're on the daily differential form of the first law. Number 1, you said you got something different than the solution.
Yeah.
Did you see a place where you thought the solution made a mistake? Sometimes there are just mistakes in those,
Yeah, I think it's just what the NASA brings out.
Oh, okay. Okay. You're probably right then. Anybody want me to go through number 1? I think usually with those solutions, the flow of the solution is right, but they'll just be like a little arithmetic mistake or something. It's just hard to get those all taken out, because just like when you get them all right, then I'll change the problems, and then the next, whatever. It's just a pain. Yeah.
Could we do 4 of it?
Yeah. And you said 3 also, right?
Well, 3 was on the weekly one, but 4 on the homework.
Okay. Anyone want to see any before number 4? Okay, sure. Let's see. Okay, so this is the differential form of the first law. So we have a transistor cooled by convection, and the outer surface has a given temperature and a given pressure, and it gives an area of what's in contact with the airflow. There's electric power going to the transistor. It gives you the H value, and then calculate the heat transfer and the temperature of the transistor's outer surface. By the way, this is super important with transistors. And if you're ever in a class in the electrical engineering lab, and you're ever sitting at the big table that's like closest to in the closest row of tables to the teacher's station, just to the left of the teacher's station, and you look on that table, there's a dark transistor shaped like burn mark on the table from it was intro class that I was in, and somebody had their transistor wired wrong, and in like a split second, this thing got so hot that it burned its shape into the table. So transistors, you got to worry about heat for sure. All right. So we know that we're going to use this form that says Q dot is equal to H times A times the temperature of the body minus the temperature of the fluid. We're given H and we're given A. So this is all in SI units. So we have 100 here. We have an outer surface area of 5 times 10 to the minus 4. And then we have we're looking for the temperature. Oh, we're given the temperature of the airflow, and we're looking for the temperature of the body. So we have like temperature of the body minus, we can keep this in Celsius because it's a difference in temperatures. We're told that it's steady state. And so the differential form of the first law says dE dt is equal to Q dot minus W dot. And this is 0 because it's steady state. And so this equation just gives us that Q dot is equal to W dot. What's the sign going to be of our Q dot?
negative?
Yep, that's right. So this is going to be less than 0. So hopefully this is going to be less than 0. Does that make sense that our W dot is going to be less than 0?
We're adding 3 watts.
Yeah, we're adding power to the system through work, and so that's a negative W. So these are both going to be negative. So let's think about, do we expect the temperature of the body to be higher or lower than 25? Higher, right. So I'm going to write this as, I'm just going to keep these signs in here. So I'll write it as negative because that fluid, the air, is cooling down the transistor. That's what it's intended to do. So, so we have negative 100 times 5 times 10 to the minus 4th power times the quantity TB minus 25. And all that is equal to negative 3. And so what we have here is that TB minus 25 is equal to 60. And so the temperature of the body is equal to 85 degrees Celsius. Does that match either of our answers? Okay, yours, not mine.
I got the A part the same as yours.
Okay.
The one relating to work.
Okay. Oh, okay, yeah.
For A, we write negative 3 watts, or because I just wrote 3.
Yeah, I guess this one you have to kind of do in reverse. So,
Just 3 watts, right?
yeah, I'd accept either one of those answers. I mean, there's not really any required sign convention for that until you decide you're going to use it in the first law. So you could say like Q dot is equal to plus or minus, plug it back into this. But we saw what the answer was as soon as we simplified this. Q dot has to be equal to W dot, so it's plus or minus 3 watts. This was actually, I wrote those wrong. This is B, and this is A. Any other homework questions you'd like to see?
Number 4 is one with the refrigerants.
Yeah. Oh, yeah. I was going to do that one anyways.
Which one is the one doing work? I think I have an idea of which one.
Yeah.
Work.
Okay. I'd say anytime you have any doubts about it, let's do it in class. That's sort of how I intend for it to go. By the way, a lot of these questions are taken from books, and the books like to throw a lot of like irrelevant information at you to exactly like the pressure in number 1. Like why are we given that? It turns out it doesn't matter in the least, But when you're really doing a problem in a research environment or a work environment, I mean, you have access to a million variables, and so you have to be the one to figure out which ones you can use and which ones you can't. Yes.
Professor, so like, wouldn't pressure like in the problem, because it's a fluid, it's convection,
Mm-hmm.
so it would matter, but it's just included in the H
Yeah.
variable?
That's right. Okay, so number 4 now. Come on. So we have 1 kilogram of a refrigerant. We're given the initial pressure, specific internal energy. It's a closed tank. What do we know from the closed tank? We know that there's no work of expansion. Okay. A paddle wheel applies, adds a certain amount of work to this material, and the rate of work is given, and heat transfer occurs. I'm going to put everything in SI units here. So if T is in minutes, I want it to be in seconds. So I'm going to do like, well, I guess I'll wait until that comes up in an equation, but we're gonna convert that so we're actually using time in seconds. 20 minutes of stirring. We have a pressure, a second pressure and a second specific internal energy. Okay, so let's start writing this stuff down. So at instant 1, we have a P1 of 0.9 times 10 to the 6 pascals if we're in SI units, and an internal energy. We know that specific internal energy is 232.92 times 10 to the third joules per kilogram. There's 1 kilogram, so we also know that the internal energy, the true internal energy, is 232.92 times 10 to the third joules. At instant 2, we have a pressure of 1.2 times 10 to the 6 pascals. A specific internal energy of 276.67 times 10 to the third joules per kilogram, and a true internal energy, since it's 1 kilogram, of 276.67 times 10 to the third joules. And okay, well, I don't think there's really actually any reason to change from minutes to seconds now that I look at it. We're just trying to figure out how much work is done. So going from instant 1 to instant 2, we know it's 20 minutes. Oh, we are going to have to calculate that.
Are we using U because it's internal energy rather than E? Just like in the
Well, it just usually those are in this class going to be interchangeable unless there's some reason clearly in the problem that speed of the system is changing or height of the system is changing. But we're going to see that, like, we're going to use tables a lot for properties, and internal energy is one of the properties that's in the table, so it's something that we're going to use quite a bit. Yes.
So to find the specific, the actual internal energy, is it because it's constant? That's why it's consistent.
Is it
Why
why do we do what?
the small u and the big U?
Oh, well, it's just given in terms of, since it was given it's a small u, which means it's specific. And also it has the units there. It's energy per kilogram. So that's a specific internal energy. But if we're going to use the first law, that has to be true internal energy. And so that's why I wrote them both down here.
So
And-
it's pretty flat, right? Just 1 kilogram. So it's
yeah, right. So they're the same numerically in this case, just because it's 1 kilogram.
Oh, the
Oh,
four.
because of.
Yeah, so to go from specific to true, you multiply by the mass. But the mass here was 1 kilogram.
Yeah, I was like.
Oh, okay. Yes. All right. So the first law is going to look like this. We're going to have so the change in internal energy is equal to Q dot minus W dot. And we can write this change in internal energy as so 276.67 times 10 to the third minus 232.92 times 10 to the third. And that is equal to closed tank. Okay, so the paddle wheel transfers energy.
so it's doing work onto the refrigerant, and that's the energy.
Well, yeah. So, shoot. Okay, so even though this section is differential form of the first law, it looks to me like it's going to set up more easily to do this in terms of the difference, the regular first law, because we have the two instants. Anytime you have the two instants, it's kind of natural to do it with the regular first law. So first I'm going to calculate the heat transfer. So over these 20 minutes, we know we have the heat is transferred at a rate of kT, and that heat is out of the system. So we're going to have negative rate times time. So we're going to have K so we're going to have like 20K and that's in kilowatts. So then we're going to multiply that again times 20. Okay, to get a total amount of energy transfer, you're always going to multiply the rate times the time. Okay, so what this is saying is that the heat transfer you're getting more and more heat transfer by rate as time goes by. And then, well, we can't just do it that way. We need to do this as an integral, actually. So we're going to do this as an integral of 20K d time as we go from 0 to 20.
So we don't have to change the time second.
No, we didn't have to.
And there's one you like the 20 minutes, or the one in the interval, not the pounds. Where 50 or 20 by
The yeah, I'm being a little careless with that integral. KT, and then okay, so let's think about this. So we have Q dot. Let me erase this for a sec. We have that Q dot is equal to KT. And then we want to integrate that So Q is going to be the integral from 0 to 20 of kt dt. Okay, so this is going to be k t squared over 2 evaluated from 0 to 20. And so that is 200k. And so I'm going to put this in here. That's a negative heat transfer, so negative 200k. And then the work is at a constant rate, so we don't have to do that as an integral. We can just think of that as 0.1 times 10 to the third times, that's in kilowatts, so that's joules per second. So we do have to think of that in seconds. So how many seconds in 20 minutes? 20 times 60. So 1200. So this is minus. W dot is negative, so this is negative 0.1 times 10 to the third. Because it's kilowatts, not just watts. And this is 1200. Okay, so now let's, so sorry, I'm running over, but 232.92. So we have 43.75 times 10 to the third is equal to negative 200 times this constant k plus 120,000. And now 200k is equal to 76,250. And so K is equal to 381.25 with whatever units it needs to be, but in SI units. So we calculated that constant K. And then you can go back and calculate part A. So the trickiest thing mathematically for sure was just coming up with the total heat transfer expression from instant 1 to instant 2. And notice that in this problem, I didn't use the differential form. I just used rates and then took those rates and turned them into calculations in the usual form. Question? Yeah.
What was the 1200? What was that from?
That was 20 minutes, but in seconds, because because that rate of work was given in terms of watts, kilowatts, and so I needed those time units to be the same.
Professor, so Q is the change from the KT and W is from the paddle wheel?
Right.
And K is 381, or how many significant figures do you want us?
I don't care about significant figures. Yeah.
Thank you.
Sure. Yes.
Why don't we have to convert it because the KT is also in kilowatts?
Because when I did that integral, KT is in kilowatts. Oh, KT is in kilowatts. Okay, I'm going to have to think about the units. That's a good question. So So where was the minutes? Oh my God, everything was in frickin'. So I think I'll need to think about those units. I think we probably have to just do that integral to 1200. But yeah, it's a little tricky. It takes a little thinking.